Hello, I'm Santosh Pandey. I'm a professor at Georgia Tech. I do research in compiler optimizations. In past, my research has focused on optimizing performance, code density, and energy consumption for embedded systems. I'll be teaching this course. Embedded systems are ubiquitous and unique in terms of their performance, energy, and real-time requirements. Both the hardware and software have unique requirements and are very different than traditional desktops or servers. Additionally, the hardware and software are very tightly coupled. The goal of this course is to understand this uniqueness and tight coupling between the two through a study of embedded processors and the compiler techniques for highly efficient code generation. In the first part of the course, we discuss embedded system processor architectures, looking at the trade-offs to achieve performance, low power, and low cost. Then we'll shift gears and discuss the special compiler optimizations for embedded systems. We'll also look at the emerging state-of-the-art solutions in this domain towards the end. Such a holistic view of both hardware and software will allow us to appreciate the deep performance optimizations that are necessary for modern embedded applications. There's a saying in engineering, you can have it fast, cheap, or good. Pick two. As you all know, this means there are always trade-offs and compromises made in one area to achieve goals in another area. For example, if we go for performance, we have to give up on energy. If we do complex chip design, costs could go up. The real question is, what are the right design choices for implementing these trade-offs in embedded domains? In this lesson, we are going to do a quick review of computer architecture, introducing basic concepts. We'll focus on the areas that will have greatest impact on embedded systems, namely VLIW and ILP, pipelines, branches, and control dependencies. However, embedded systems are different. The three key goals of embedded systems are low power, high performance, and low costs. And so keep in mind how these unique design point features may be affected as you refresh your knowledge of computer architecture. Okay, for a 2003 Volvo, the answer is 50 embedded processors. And the right answer for 2003 Mercedes is 100 processors, in fact. Take a look at the link in the instructor notes that actually talks about number of embedded processors in different types of cars. So the key question is, what is the purpose of so many embedded processors? What do they do? Why should they be different? Let's take a look at simple car metaphor. First, the car's engine should run at the best efficiency. The gas prices are high. Second, braking should be coordinated with speed, curve, slope, and traction to avoid skidding. And third thing, in luxury cars, the temperature should be maintained, tracking the outside conditions. You don't want to walk in a frozen car in a snowy day. Some typical characteristics desired from embedded processors are real-time performance, extremely high performance, very low energy consumption, otherwise battery will run out in no time, and finally very low costs. There are hundreds and thousands of processors, so the cost should be dime a dozen. So how to meet these simultaneous requirements is a big question. The requirements can't be simultaneously met by traditional processors, which are energy hogs. In fact, an egg can be fried on a server class chip and they are not cheap. Let's check out the link in instructor's note. You can see that a guy is able to fry ham on his processor. The first requirement of high performance is met by instruction-level parallelism that allows executing multiple instructions simultaneously to increase performance. There are many forms of instruction-level parallelism. The different forms of instruction-level parallelism manifest as superscalars, in-order processors, VLIW, and in- and out-of-order execution. The correct answer is VLIW in-order processor design is the most preferred design choice for embedded processors. The reason for that is multiple instructions in a slot lead to better performance. Meeting the performance characteristic, execution is the most energy efficient execution. Since multiple instructions are issued in the same cycle, energy spent in instruction issue is further reduced, and that's why VLIW in-order is the best choice. In order to understand the requirements for embedded processor design, let's do a quick overview of VLIW, superscalar, in and out of order processors, and you should be able to figure out which architecture would be better for embedded systems in particular. In VLIW, a single instruction is loaded, but it consists of multiple sub-instructions that execute in parallel. Each sub-instruction is a simple RISC instruction, and multiple sub-instructions are loaded at once. Unlike VLIW, only one instruction is issued in a cycle in superscalar. Instructions that execute in the same order they are issued are known as in-order processors. Instructions that execute out of order with regard to their issue are called as out of order processors. So multiple possibilities exist. Let's test our knowledge about these different possibilities through a quiz. So the best possible processor design for embedded processor, is it superscalars in an out of order execution style, or superscalars in an in order execution style, or VLIW in an in order execution style, or VLIW in an out of order execution style? You can see that we have different choices and different combinations of these choices. Let's now review the instruction level parallelism that you know from computer architecture course. This is a 5-stage pipeline from RISC machine. As you can see that in each cycle, the processor can execute one of the 5 instructions: instruction fetch, instruction decode, execute the decoded instruction, memory access to get the operands, and finally write back to write the results back to the memory. ILP allows different parts of different instructions to be concurrently executed in a given cycle, which speeds up its execution. Let's review the foundations of instruction level parallelism. First of all, ILP is a program's property. The number of such instructions that can be concurrently executed depends on the program. Some programs have higher ILP, some programs lower. ILP is a concept independent of hardware improvements such as faster clock frequency or faster memory, amongst other things, and can always be coupled with any generation of technology. And finally, ILP is all about multiple operations that can be executed simultaneously within a clock cycle through different parts of hardware. So how the concept of ILP is different in embedded systems? Remember, the biggest constraint in embedded systems is energy or power, and there is a trade-off between performance and power. ILP allows maintaining the same performance due to parallelism, and more parallelism allows decreasing the clock frequency and eventually the energy. How is frequency related to energy? The greater the energy, the larger the frequency, and the shorter the wavelength. Roughly, the relationship can be seen as 1/E is proportional to f square. So if we decrease the frequency by half, we will save energy 4 times. Energy is inversely proportional to the square of frequency. Typical pipelines in modern high-performance processors are anywhere from 15 to 20 stages. For example, Pentium 4, the last of non-multi-cores, had 20-stage deep pipeline. Sandy Bridge and Haswell has scaled it down to 14 stages. A good question to ask yourself: why are processors scaled down to 14-stage pipelines after all? Let's test our knowledge of ILP. So here is a question: how deep are the pipelines in modern high-performance processors? Is it 5 to 7 stages, or 8 to 10 stages, or 100 plus stages, or 15 to 20 stages? Let's first understand sequential execution of instructions. Typically, in every clock cycle, we could issue a new instruction. So we would expect an execution of one instruction per cycle, but in reality, many instructions take more than one cycle to complete. Loads and branches are notorious and can take more than a cycle. Unless one instruction completes, the next one cannot execute, since it has to wait for the results of the previous instruction. As you can see through this particular example, the value of A is not available until the end of this particular cycle. The value of B is not available until the end of this particular cycle. And therefore, the add cannot happen until the new values of A and B are available until this particular cycle. Sometimes an instruction keeps processor resources busy even if there is no dependence on its results. Due to the above reason, in practice, we have less than one instruction completing on an average per cycle. Let's understand the ILP for sequential semantics in a single thread. The processor tries to issue an instruction every clock cycle, but there are dependencies, control hazards, and long latency instructions. Due to these dependencies, delays result in execution, and there is an execution of less than one instruction per cycle on an average. Instruction level parallelism, also called as ILP, is achieved by executing multiple instructions in a cycle on the other hand. One of the key measures of ILP is instructions per cycle, IPC, which defines how much concurrency we can achieve by executing multiple instructions on an average in a clock cycle. Strict sequential semantics results in low IPC due to lots of dependencies. Low IPC is mainly due to instructions stalled for data and resource release by other instructions. On the other hand, if we can keep the pipeline fully busy executing the instructions, maximally overlapping them, we can achieve the IPC to be nearly equal to 1. That is the principle of ILP, and that is how we can complete one instruction in every clock cycle. To illustrate the ILP IPC concepts, let's go over a VEX program. The first instruction is a load instruction that loads a value from memory, followed by 2 no-op instructions. This is followed by a compare instruction, which compares the loaded value with 0. Following that, there is a branch instruction that jumps to a label done, Following this again, there is a load followed by no ops, followed by subtract, and so on. First question that crosses our mind is, what is the purpose of no ops? The main purpose is to add a delay so that the load instructions are available for the compare instructions in terms of their results. Load instructions take 3 cycles since data may not be present in a cache. Similarly, compare instruction takes 2 cycles, and to fill in these delays when the results of those instructions are available, we are inserting no ops. The same program now is shown in terms of this table here, which corresponds to which instruction is executing in which clock cycle. One can see that the load takes 3 cycles and compare takes 2 cycles. If the above program were to execute in a sequential manner, it will totally take 11 cycles to complete as shown. So now let us calculate the IPC for this particular simple program. As you can see, there are 6 VEX instructions which execute in 11 cycles. And if we were to calculate the number of instructions that are executed on an average in a cycle, that will be 0.55. That means on an average, every 2 cycles we are able to finish 1 instruction. What this also means is, since we are able to complete an instruction in every alternate cycle, the cycle in which we are not able to complete an instruction is sort of wasted. As you can see here, the instruction is complete in every other cycle. That means it takes 2 cycles for an instruction to complete. So every other cycle is wasted here. That is what is shown by this particular sequential execution. Having seen the sequential way of execution, let us see how now the pipelining is going to help us in terms of overlapping the instructions. So as you can see in these particular diagrams, here is the first execution that is shown, which is non-pipeline, which is sequential. Each instruction first completes and then only a second instruction starts over here. After it completes, the third one starts there, and then finally fourth one starts here and completes here. If you had to pipeline to take advantage of overlapping of these instructions, you can see that the first instruction starts here in the first clock cycle. The second instruction doesn't wait all the way until the first instruction completes, but it really starts at the second cycle, and then the third one starts at the third cycle, and so on. So instruction level parallelism is facilitated by the pipeline instruction as is seen here. Each instruction goes through several execution stages. Each execution stage has a resource associated with it. A later instruction can share the resource which is used by the previous operation in a previous cycle. Like for example, this second instruction over here is sharing the resource of fetch, which is used by number 1 in the previous cycle, and so on. A given instruction streams through a pipeline and goes through k execution stages for k stage pipeline, taking k cycles to come out. Thus, in a given cycle, each stage of the pipeline is occupied by different instructions, and thus the instructions overlap during their execution. So now let us see how the pipelining works in terms of the execution stages which are used by the different instructions. First off, the execution stages are divided into several steps. A later operation can share the resource used by the first operation in the previous cycles. Shared hardware can be pipelined. For example, integer multiplier is pipelined and is used by several instructions in different stages. And this facilitates the instructions can be overlapped, because an instruction can use one resource in one cycle and another resource in another cycle, and different instructions can use different resources in different cycles and share them. And the answer to that particular question can be found in terms of the cycles it takes per instruction as follows. So the cycles per instruction is calculated as follows. Here we have 50% of the instructions as R type, each taking 4 cycles. So that is why 50 times 4 gives us the total number of cycles which are needed for R type instructions. Similarly, 10% of the instructions are load instructions and they take 5 cycles. So we have 10 times 5 total cycles for load instructions, 20 times 4 cycles for store instructions, because we have 20% of the instructions as store, each taking 4 cycles, and then finally we have 8% instructions as branch, each one of them taking 3 cycles, and then similarly we have jump instructions which are 2%, each taking 3 cycles. So out of 100 instructions, this is the breakdown here multiplied by the respective number of cycles. So that is the total number of cycles it takes here for this particular program. And then there are 100 instructions here. This particular program has 100 instructions, so that divided by this is 3.6. So roughly we have 3.6 cycles per instructions for this particular program in a sequential execution. Note that IPC or CPI is specific to a program because it really depends on the mix of these particular instructions, and it is also assuming here that we have these kinds of latencies on these machines and they are executing in a sequential manner. So having seen the concept of sequential execution as well as pipelining, now let us see how we can calculate the instructions per cycle for a sequential execution. The instructions per cycle for a sequential execution really depends on the instruction mix and the number of cycles each of those kinds of instructions takes. For example, here the load is taking 5 cycles, store is taking 4 cycles, an R-type instruction is taking 4 cycles, the branch is taking 3 cycles, and the jump is taking 3 cycles. So this is a typical MIPS kind of a multi-cycle machine, which is if it executes sequentially, then we want to see a particular program how many cycles it takes per instruction. So let us say a program has 50% R-type instructions, 10% load instructions, 20% store instructions, 8% branch instructions, and 2% jump instruction. Then what is the instructions per cycle for this particular program? Or conversely, what is the total average number of cycles it takes per instruction in a sequential execution? That's the question, and let's see if we can answer it. Before we actually calculate the IPC or CPI for pipeline execution model, let's kind of understand it at a higher level in terms of different stages. So here is the basic pipeline. The basic execution of an instruction inside the processor typically follows 5 basic stages. First, the instruction is fetched from the instruction cache. Next, the instruction is decoded to find out what this instruction is all about. Then the instruction is executed. Typically, the execution happens using the registers, or the address is calculated for fetching the memory operands. Some instructions need memory, so they do the memory access in this particular stage. And finally, the results of the execution of the instructions are written back in this last stage called write back stage. They are either written back to the memory or they are written back to the registers. As you can see, for this pipeline, after the first instruction enters the pipeline, it will take 4 cycles after that for the instruction to come out of the pipeline here. Having understood the basic pipeline, now let us see if we can find out the execution of the instructions that stream through them. As you can see here, the different instructions stream through this pipeline following each other, and it does take some time to fill up the pipeline because one of them is going forward, then the second is following it, and the third is following it, and so on. And all the stages of the pipeline, which are about 5 stages here, it takes a certain number of instructions to fill them up. So our quiz is this, that if we were to observe the end of the pipeline, how many cycles initially will not see a single instruction coming out? And let's assume a k stage pipeline for a general purpose here. Is it going to be k? Is it going to be k minus 1, or is it going to be 2k? How many cycles will not see a single instruction coming out? Let us now understand a different type of an instruction level parallelism which is exhibited by our VEX architecture. The VEX architecture implements a different form of instruction level parallelism called VLIW, in which multiple sub-instructions are packed into one which execute in parallel. VLIW is called Very Large Instruction World. There are major restrictions on which sub-instructions can parallelly execute together in VLIW. The instructions should not have dependencies, nor they should share resources. In VEX, there is only one memory operation allowed in each slot. This is so because there is only one memory unit available in the processor. One other interesting part of VEX is it allows dismissible loads which could be hoisted above the branches. In other words, the loads could start early before the branch outcome is known. This is done so that we can take care of their latencies without waiting for them. So what is a dismissible load? A load starts executing early without waiting for a branch, and then once the branch outcome is known, we either commit the load or we throw away its execution. As discussed earlier, the loads also have latencies, and therefore we need to worry about allowing substantial number of cycles before we can start using their results. So the first load in that example, load B0, takes 3 cycles, and in order to wait for the load to complete, we have to exert 2 no-ops in that particular example, as you will note. This was the case in sequential execution where the no-ops were doing nothing and just wasting cycles. But in VLIW now, let's see how we can take advantage of this. The loads B1 and B2 could be now inserted in slots 2 and 3 because we can start executing these particular loads which are not really dependent or anywhere related to the load B0. We could not put, of course, load B0 and B1 in the same slot because again only one load is allowed in a particular slot. You can see that in this particular example, the load in slot 1 is a regular load, whereas the loads in slots 2 and 3 are dismissible or conditional loads. Let us now consider the parallelism part of this particular example for the VEX architecture. You can see a program in the instructions note. As you can see, we can have maximum of 4 sub-instructions inside an instruction. Each instruction executes in a given slot. Slots execute sequentially, that is, slot 1 executes, then it is followed by slot 2, then it is followed by slot 3, and so on. So the question is how these instructions which are here can be placed in these particular slots for maximizing their parallelism or minimizing the time that it takes for this program to execute. Recall that we have restrictions. We cannot put more than one load in a given slot because we have only one memory unit, and we cannot put 2 instructions in one slot which have dependencies on each other, which needs results from one by the other. So given these restrictions, we can perhaps put a load and a compare instruction, or load along with some other instruction which is not a load in each of these slots. For this particular program, however, we can see that we have to follow a particular schedule because of the dependencies and so on. So in the slot 1, 2, and 3, we are able to only place one load, since 2 or more loads in a slot are disallowed because of just one memory unit that is present on the machine. One can see that a load and a compare instruction can perhaps go together in a slot provided they do not have dependencies and they are allowed to be in that particular slot, or nor they share the resources for which they have to contend. So as far as this particular program is concerned, the schedule will be that the first load goes into this slot, the second load goes into this slot, second slot, the third load goes into the third slot, and in the fourth slot we can arrange this fourth load and a compare instruction together. The answer is that it needs the results of the load instruction in the first slot, which is in R20, the register R20, which is not available for 3 cycles due to load latency. Similarly, compare in slot 5 can't be moved any earlier either. We can also see that we can put as high as 3 instructions together in a given slot, but for this example, we are unable to fill 4 instructions in a slot. So what is the advantage of VLIW over pipelining? The advantage is this, that in VLIW we have multiple instructions that can execute concurrently in a given cycle which are in a given slot. But the disadvantage is that many times we cannot fill in multiple instructions in a given slot. Rarely we are able to use all 4 instructions inside a given slot, for example. So you might be wondering why we could not put this compare instruction that is currently in the 4th slot in any of the earlier slots. Naturally, it will be beneficial to move an instruction as early as possible because then the program can complete much faster, and that's the goal of the scheduling. So now let us see how we are able to fill up these instructions inside respective slots given all these restrictions and dependencies and so on that we have already discussed. First off, the first load can go in the slot 1, but the second, third loads cannot go in this same slot because there is only one memory unit. So we have to put the second load in the second slot, third load in the third slot, and we continue this process. The fourth load will go in the fourth slot. Note that these are dismissible loads because they are dependent on a branch condition, and unless the branch conditions is known, we cannot commit the results of these loads. So that's why they are dismissible loads, which are marked differently than the regular load over here. When we go to the fourth slot, we have a dismissible load, and then we have a branch condition, and you can see that this particular branch condition needs the results in R20, and that's why we had to wait for 3 cycles in between before we could schedule this compare instruction over here, which depends on the results of the first load. In slot 4, now you can see that we cannot fill in 2 other instructions here because both these instructions again need some other results and they may not be available until here, and moreover there could be a restriction that this load and second load cannot go together in the same slot and so on. So because of these reasons we had to wait till the next slot for scheduling this load, another branch, and so on, and we continue this particular process. Wherever possible we can schedule an instruction which is ready latency wise if its results are available in so many cycles and it is not conflicting on the resources and it doesn't have any dependencies on other instructions which are scheduled in this particular slot. So for example, in slot 6 we have now 3 instructions which are scheduled. Similarly, we follow the program and we keep scheduling these instructions in different slots For example, in slot 9, we schedule this add instruction here, and we could do so here because it did not have any dependencies which were unresolved. It had all its operands ready given the latencies and so on. For example, this load has to complete for 3 cycles here before the value is available in R24. That's why we could schedule it only after this, and we ended up scheduling it over here. Similarly, the sub instruction could be scheduled here in the same slot because again it doesn't have any dependency on this add instruction here, and moreover sub and add do not conflict in their resources and so on, unlike the load instructions which only one of them can be there in a given slot. And we continued the process and filled in a branch instruction here in slot 9, and we continued this particular process for slot 10 for scheduling this add instruction. Having done this scheduling, now let's look at the IPC that we will get because of this schedule, the instructions per cycle, how many instructions we will be able to finish in a given cycle. You can see that we have 18 instructions here total, and we have been able to place those in 10 slots obeying the latencies, resource constraints and so on. And thus we are able to get the IPC of 1.8, a major improvement from the IPC of 0.55 for the sequential program of the same instructions. Note that many slots still have only a single or a couple of instructions than the full potential of 4 instructions. In fact, the maximum number of instructions that we are able to place in a given slot are just 3, not 4. And which is the case, and that's why the width of the VLIW architecture, that is how many instructions could go in parallel here in a given slot, is carefully decided. It should not be too small because then we'll have more parallelism which is untapped, and it should not be too wide because then there will be a lot of empty slots which are left out for which we are paying the price of energy. So this is a clear trade-off between the energy in terms of the width being as small as possible and the parallelism claiming that the width should be as large as possible. And the answer is 4, because we could, in an ideal world for a given particular program, we could fill in all 4 slots with the available parallelism, and so we could process 4 instructions per cycle. So that's why the IPC that is maximally possible could be 4. Again, note that this is rarely the case because we can populate these slots at most with 2 or 3 instructions, not 4. So the realized IPC is much lesser than the width of the slots. So now let us test our knowledge in terms of the maximum IPC that could be possible in this VLIW architecture of 4 sub-instructions per slot. So what is the maximum IPC that is possible? Is it 2 or 3 or 4? So far we saw that one of the biggest sources of problems for IPC degradation is these loads. They claim a slot and then nobody else can come in that slot. That is, another load cannot come in that slot, and the loads take a lot of latency to execute, which means they delay other instructions. Are the loads the only source of problems? Another big source of degradation in IPC is branches. In the absence of a branch, instructions are streaming through the pipeline and they are fetched in sequence as shown here, one after the other. However, at the point of a branch, it is unclear which direction the execution will proceed and therefore which is the next instruction that should execute. Maybe if the branch is not taken in that particular direction, I4 will not be that particular instruction, and therefore we have to worry about getting a different instruction. So for example, the instructions are streaming one after the other, and in this particular example, instructions I3 and I4 have already entered the pipeline, but they are for a branch that is not taken, and they must be removed from the pipeline, and the taken branch instruction should be executed. So these instructions should be nullified. In other words, before a branch outcome is known, we do not know which instructions should be executed based on that outcome. If we, however, wait until the branch is resolved, it is too late, and this causes a bubble in the pipeline due to the absence of any instructions. For example, in this case, if we wait slot 5 or time 5, we are not able to do anything. In slot 6, we'll then say that, okay, let's start with the instruction IA, and we would have wasted some time here, and because of no instructions in slot 5, now that bubble will keep progressing into the later stages of the pipeline and no useful work will be done. On the other hand, if we bet on a path and prefetch a particular instruction, upon misprediction, we pay a huge penalty to empty the pipeline. So for example, if we got a wrong instruction like this I4 and I3, then when those instructions are already in the pipeline, they would have done some work, they would have taken resources, put results in some registers, and all that needs to be cleaned up because those were the wrong instructions to begin with. Refer to the instructions note for details on this bubble as well as the penalty of flushing the pipeline. So let us recap what happens in a branch, especially in the pipeline. So uncertain paths cause bubble in the pipeline. If we take a wrong path, there's a lot of penalty because we have to flush that pipeline with the instructions that are not intended to be there. Easiest way is putting a bubble or a delay slot to resolve a particular branch, that is, wait on the resolution of the branch. But putting such a bubble or a delay slot means we are going to waste some cycles. So what is the solution here? Some independent operations can be inserted in the delay slots to make use of those. In order to reduce or avoid misprediction penalty, many times we have branch predictors in processors. Such a branch predictor is expensive for embedded systems though. Alternative is to be able to move branches up in the control flow and fill the idling slot with instructions that would definitely execute regardless of the branch outcome. This is a preferred solution for embedded systems, and it does not need extra hardware, and it also uses those branch or delay slots by carrying out some useful operations. The correct answer is in fact 4. That is, both A and B are in fact responsible for the limitation of this approach. In some cases we are unable to move the branches up, whereas in some other cases, even when we can move the branches up, there are no available operations or instructions that could be scheduled in the delay slots. So why are we unable to move the instructions up? Well, the main reason is dependencies. An instruction can't be moved up above another whose results it needs. Again, due to dependencies, sometimes we can't find enough independent operations or instructions to fill up the empty slots. So together, these two reasons are sort of posing limitation to an approach of using a delay slot and by moving the independent operations into the delay slots. So now let's see if we can discover the limitation of the branch movement approach. What would be a potential limitation of the move the branch up and fill the delay slot approach? One alternative could be we can't move the branch up much. In many cases it can't move up at all. In some other cases, we can't find enough operations or instructions to fill the delay slots. So the question is it only that A is true, or is it that only B is true, or neither A or nor B is true, the reasons are totally different, or both A and B are in fact responsible for the limitation of this approach? What is the right answer? We saw that dependencies are at the heart of the problem in terms of using the delay slot or not being able to use the delay slot, to be more precise. So then let's find out what are the different kinds of dependencies and what do they represent. So we have two types of dependencies, control dependence and data dependence. The control dependency is straightforward. It tells us whether or not to execute an instruction or a group of instructions based on the control flow in the program. For example, a branch evaluating to be true means all the instructions on the false side of the branch are not to be executed and the ones on the true side are to be executed. All of these are therefore said to be control dependent on the branch. Data dependence, on the other hand, puts an order of evaluation on the program. A dependent instruction B cannot be executed before an instruction A it depends on. There are three kinds of dependencies. True dependence occurs when instruction A feeds data to instruction B. It is easy to see that unless the data from instruction A is available, B cannot execute. So here is an example of a true dependence. An instruction A is generating data in register R1, which is to be used by instruction B from the register R1, as you can see. So unless the data is available in R1, instruction B cannot progress. And this is an example of true dependence of instruction B on A. The second kind of dependency is write after write. Both instructions A and B write to a given location and they must do so in the program order, else we'll see different data in that particular location in different order. Here is an example. We have an instruction A writing to a register R1 and instruction B is also writing to register R1 in that particular order. That is, first A writes to R1 followed by B. Now if we interchange these two instructions, we'll see the different values in R1 at different points, not in the same order at which this particular instruction should be showing the value earlier than that one. So that is why this is a dependence, which means that instruction A should precede instruction B. And finally, we have a third type of a dependence, which is called as var dependence. That is, an instruction cannot override the data of a prior instruction until the prior instruction that is reading the data is complete. In this particular example, instruction A is reading the data So the instruction B cannot overwrite it and must wait for A to complete. This is a war dependence. Can you identify which is that register which is being read so that it should not be overwritten? Obviously, as you can see it here very clearly, that is register R2. Before R2 is read by instruction A, it cannot be overwritten by instruction B in the next cycle. And that means that A must complete before B can start. We saw three different kinds of dependencies, and they pose severe problems in instruction scheduling. So the question is, how can we minimize those dependencies? Several techniques are in fact designed for addressing the dependence issues, especially with regard to control dependence. The first technique is speculation. We can speculate to avoid having to wait for branch condition. This avoids control dependence. We can go ahead and start executing this sequence of instructions, and when the branch condition is known, we can either commit their values or we can discard them. But one of the important parts of this solution is that it needs a branch prediction approach to avoid penalties for misprediction, because remember, still there is a work to be done. When there is a misprediction, we have to discard all those results. An interesting way to implement speculation is by using what we call as predication. That is, keep executing all those instructions one after the other, but tag their commit with the branch outcome. That is, only in the last stage of the pipeline, all those instructions are held back, and in the write back part of that instruction, they are not allowed to go forward unless and until the branch condition is known. When the branch condition is favoring the execution of that instruction, the write back stage is triggered and the instruction commits. When it doesn't, the instruction is discarded along with all of its work. Finally, as we were seeing in the last couple of slides, a lot of data dependencies are because of write after writes or write after reads. Now note that these are not true dependencies. In other words, they are because we haven't finished reading a particular register or we haven't completed a write to a particular register. What if we have lots of registers to use which can write to independent places so that these dependencies simply go away? After all, they are false dependencies. So the data dependencies, which are VLIW and VAR, can be addressed by using different registers and by using register renaming to avoid conflicts. That means those two instructions are reading and writing data from different registers, and therefore they need not wait on each other. So remember again, which is the dependence which cannot be removed by this register renaming technique? The dependence which cannot be removed is true dependence. Because remember that an instruction must wait for the results of a previous instruction because it needs it in computing its values. And that's called as true dependence. And that problem cannot be solved by register renaming, and that is why this dependence is called as true dependence. The correct answer is B. That is, the instructions in S3 are not control dependent on P. The branch outcome in P, whatever it will be, does not affect execution of S3, as you can see here. S3 always executes regardless of whether P is true or false, and so it is not controlled quote unquote by P, and therefore it is not control dependent. Unlike data dependence, control dependence never depends on what exactly S3 is all about. It doesn't depend on its operands, it doesn't depend whether they need results from a different place or whether they should be read before they are written, and so on. And so the answer C is not even relevant to the question of control dependence. Control dependence is purely decided by whether a predicate P controls execution of a given statement in one direction versus the other. So statements S1 and S2 are control dependent on P but not S3. So now we should have a good understanding of data dependence. But let us see how clearly we understand the control dependence. Consider the familiar example of if-then-else statement and a statement following that in this particular block. The question is, are the instructions in S3 control dependent on the instructions that evaluate the predicate P? You can clearly see that if the predicate is true, S1 executes. If the predicate is false, S2 executes. But the question that we are asking is S3 control dependent on this particular predicate? Now what is S3? S3 is a statement which is outside the if-then-else statement. It is the one which is immediately following it. We have three choices here. Yes, it is control dependent. No, it is not control dependent. And maybe, it really depends on what S3 is, the content of S3. If S3 has something in it, maybe it is control dependent. If S3 has something else in it, maybe it is not control dependent. That's the third choice. So far we have been talking about pipelining and VLIW, which is a special type of a parallelism used in embedded systems. But what are the other kinds of parallelisms which in general exist, and are they relevant or are they useful for embedded system? That's the question to be answered. Apart from instruction level parallelism, other forms of parallelism include vector processing, in which there is a special vector function unit and a register. For example, one could have a vector add operation, and one could add two long streams of data using one such instruction. Vector processing is good for scientific codes which are regular. However, vector processing is not good for irregular codes and short vectors. Moreover, vector processing is expensive because you have to support special types of registers, special types of function units, and special types of operations, and they can be energy hogs. And therefore, vector processing is rarely used for embedded systems. What are the other types of parallelism apart from vector processing? One of them could involve multithreading and multiprocessing. One of the important forms of multithreading is called as simultaneous multithreading, in which the same ALU is shared by two different threads interleaving their instructions. So the question is, how does it work or how is it implemented? Each thread has a separate set of registers, but they share function units, and therefore the chip is somewhat simpler and is not very high in terms of energy consumption. However, as you can see here, you must have still separate registers, and you must save those registers or context switch between different threads and so on demand if you're sharing some registers. And therefore some overheads can become high here. And so again, this approach has to be very cautiously employed for embedded systems. Yet another form of parallelism is called as micro-SIMD. What is micro-SIMD? We have a single instruction and which operates on a lot of multimedia data which is packed in a particular register. Remember that unlike vector processing here, there is a single register and each register is packing multiple pieces of data here. In vector processing, we have multiple registers, each with separate piece of data. So this instruction operates on multiple data but inside a single register, and that's why this is energy efficient over vector processing. As the workloads keep increasing in embedded systems, for example, many modern smartphones need now a lot of processing power on multiple pieces of data. So the solution of micro-SIMD is slowly being adopted in many embedded processors, especially those which are deployed inside smartphones. Sometimes we do have multiple chips which are doing multi-processing, like in modern iPhones, you have dual core or quad core chips and so on. So some of these demands are growing in terms of the processing power, but again, each one of those cores has to be very simple. The function units are shared, the registers are kept separate, and that's why it is a low overhead, low power chip still, which is being used in embedded systems. Unlike servers, where some of these solutions could be developed without paying any attention to energy or number of resources, and they are purely optimized for performance, the embedded systems have these solutions adopted, but with a very light amount of additional resources, and definitely by keeping the energy consumption as low as possible. Well, we have reviewed traditional computer architecture, and now we are going to see how things are quite different for embedded systems. After viewing this lesson, you should have some inkling as to which areas we are going to change and why. Here is a hint. Which processor features affect low power consumption, result in improved performance, and have a low cost, and how do they affect these parameters is what we need to focus on.